No, we aren't. Okay, now we are.
Awesome. Cool. We're going to go ahead and get started. So, hey everybody, this is the introduction to quantum computing. I'm going to say this is a brief introduction to quantum computing. This is not going to be a deep dive, so don't worry if you're like kind of intimidated if you're walking in here. There's no math, and the live coding portion I think is going to be kind of fun. I started a new job last week, and I'm kind of getting a repetitive strain injury, so I can't actually type much, but we're still going to do some live coding, and I'm kind of excited to show what exactly that's going to entail. So a little bit about me. Like I said, I graduated Ucf last semester. One really important thing, I don't do quantum computing as my day job. I'm just a full stack dev. And math is one of my weakest subjects. So if you're intimidated by quantum computing because you've heard, hey, there's a lot of linear algebra involved, which there is, don't be. It's promise you can actually learn this subject. If you're still an undergrad and you haven't taken your 2 math courses yet, definitely take linear algebra as one of them. I never did that. I wish I did. It's great for programming interviews, and it's super helpful for so many other fields of software engineering, like machine learning, just general like distributed system stuff, quantum computing now as well. So there's a lot of cool stuff you can get out of that course if you're able to take it. So we're going to start off real quick with a super brief review of classical computing. So classical computing is the computing we use now. It's standard everyday computing. It's what I'm presenting these Google slides with. It's what you're watching Zoom on. Classical computers essentially are just, as we know, 0 and 1s. And they all operate on transistors, which is just like the lowest level hardware piece. And one of the fundamental building blocks of like logic gates of classical computing is known as the Nand Gate. If you haven't taken CDA yet, which is one of the kind of intro to like hardware courses, like hardware software courses here at UCF, you kind of take it around the same time as Intro to C and Discrete 1. That's perfectly okay. Right over here, where's the little pointer? I don't remember where that is. But right over here is A and B, so 0 is false, so false and false equals false, but we have a NAND gate, just does a not on the operation, so whatever the outcome of this is, the opposite of that. So 0 and 0 is false, so this is true. That's basically all you need to know for classical computing to kind of get started with quantum computing right now. So before I kind of roll into quantum computing, I want to go ahead in the chat, go ahead and write what you think quantum computing is. Because there's definitely, I didn't know what it fully was when I started learning about it. So it was, magic is a good answer. That's partially correct. So write your answer in the chat. It'd be interesting to see if anyone can kind of get their misconceptions shattered or kind of their mind blown like I was when I first learned about it. So, yep, Mykola, I hope I'm pronouncing that right. It's something to do with qubits, something involving electrons. It's another one good one. Conroy says, I always thought it was complicated math. I do have to unfortunately tell you, it is complicated math if you want to do it. But it's math that if you're doing quantum computing, you'll feel comfortable with it. So there's no math in this presentation specifically, or very little. But actual quantum computing is very low level. So the simple Wikipedia definition of quantum computing is just a computer that uses quantum mechanics to perform computational tasks. So a quantum computer is not like some amazing new branch of computing. It still uses a lot of takeaways from classical computing, as we're going to see, to help run its task. So if you know a little bit about computing history, you know, like computers are Turing complete is what it's often heard as. And if you'll learn more about this in Discrete 2 when you take that course, I'm going to assume not a lot of people are following the degree, so I might make references to classes that people haven't made yet, and I'll try to explain those references along the way. But quantum computers don't have like many additional capabilities over regular computers, and we're going to see what additional capabilities they do have and why would we want to use them and what applications they have. So here's a brief list of applications for quantum computing. I listed them like from some of the ones I find most interesting to some of the more boring ones. This list is normally reversed. When people talk about quantum computing, they normally talk about how it's going to have solving all these hard problems, and it's going to break modern cryptography, and all the hackers are going to get into your bank accounts. I don't care about that stuff. I don't find that very interesting. I think it's so cool that quantum computing lets you search a list of n items in less than, like technically less than n time. That is so much faster than we can do in classical computing. I'm not going to show what that is in today, like in the code examples, but if you're interested, it's called Grover's search or Grover's algorithm. Super cool stuff. Other cool things that quantum computing can do, it's not 100% proven yet, is drug discovery. So a lot of drugs and biology operates on like the physical level, especially biochemistry, on like the proton and atom level. And if we can simulate those quantum systems, because that's what they are, they use atoms and everything, use quantum mechanics at their core. If we can simulate those systems, we can accelerate drug discovery and help find more drugs for more illnesses and ailments and other types of physical simulations. Another one is machine learning. So machine learning, this is a really interesting connection. Machine learning involves a lot of linear algebra as well as quantum computing. And so the connection between them is just that they share a lot of the same like math. And that's like the only connection. It's not like machine learning and quantum machine learning is just kind of more efficient. It's not commonly used, but if you use TensorFlow, which is a machine learning library, they have a TensorFlow Quantum that you can use as well. So if you want to experiment with that, you can open up the TensorFlow docs and check that out as well. They also make that pretty accessible. And the other two that I mentioned, breaking modern cryptography applications. And the really interesting one, solving hard problems that would normally take forever on a classical machine. We're not going to really go into that today, but that's normally when people talk about quantum computers, that is the example they give. This term right here, quantum advantage, it's often called quantum supremacy. But quantum computer scientists, they have some disagreements. Should we use the word quantum supremacy? Because when someone hears the word quantum supremacy, they think, oh my God, that's such a big deal. When in reality, when someone says Google achieved quantum supremacy, I think last year in 2019, and all that means is that Google solved a problem on a quantum computer that a classical computer would take eons to solve. A single problem. When I first heard of quantum supremacy in the news article, I thought, oh my goodness, that's it, we solved quantum computing, we did it. No, they just found a single problem that they were able to successfully run. And it's pretty uncommon, actually. We haven't achieved quantum supremacy in many tasks yet. So oftentimes you'll hear it called quantum advantage, and that's the term that's slowly starting to be adopted more. So when I asked my friend who is a quantum programmer, he said he recommended to use that term in these slides. So someone mentioned earlier qubits. So as you know, with regular computing, you just have classical bits, which can be 0 or 1. Qubits are essentially like an atom, quite literally an atom. They can be 0 or 1, or they can be a complex number. If you remember a complex number from high school algebra, you thought I would never have to see them again. That's a lie. They're back. This is the first time I've seen them since out of high school. But essentially, they can be 0 or 1 or anything in between. They can be in this big continuous space. Another thing, they can also be in other dimensions. So you have the x, the y, and also z. And that's going to be relevant when we talk later about some other things you could do on qubits. But qubits can operate they have a much bigger state space. So they can not just be 0 or 1, but they also be in this complex number space. One important thing to note is that they'll always end up in 0 or 1. So like I was mentioning before, quantum computing is just an enhancement to classical computing. So whenever you're actually running quantum computing programs, yeah, this complex number space is really cool, but you can't use it for any problems. We'll see how we do use it in just a second. We'll talk about superposition and entanglement and teleportation. But when we're actually kind of running the calculations and measuring the results, they're going to collapse to 1 or 0. And this is the really cool part about quantum computing. So another really important thing, this equation is going to come up a lot, so just remember it. And if you need to know what this notation is, this is going to be the most math you have to deal with, these double straight brackets, normally seen in absolute values. It just means the length of a vector. So I was mentioning this is 3D space. And anytime you operate in a plane with multiple dimensions, you normally talk about that in vectors. the XY coordinate system, like this is just components of a vector. And that's going to be like the most math jargon we're going to use today. And if anyone has any trouble with that, you can ask those questions in the chat. Don't feel intimidated if your math knowledge is really rusty and you feel like, man, I don't even know what he's talking about there. That's perfectly okay. I was at that point too in college. I started off college in remedial math, so don't feel like embarrassed to ask those questions. There's no stupid question for this. So yeah. I'm going to represent quantum bits, qubits like this today. Each of these is a single qubit, so this is a pair of qubits. Normally you won't see them represented like this. When you see them in textbooks, they're going to be represented like this little angle brackets. This is called Dirac notation, but we're not going to be going into that too much today. So we're going to start getting to all the cool quantum mechanics stuff and all the cool stuff that makes quantum computing after we had this little brief introduction. Before I start, what do you think superposition is? So people who you might have heard of Schrodinger's cat. That's one of the most common and famous examples. If you don't know what that example is, it's essentially if you put a cat inside of a little thing, inside of a room that also has, the actual story is a little dark, so I'm just going to put, if you have a cat that's inside of the room, you don't know if the cat is sleeping or awake until you open the door and you measure or you see what the cat is. But while that cat is in the room and not being observed, it is both awake and sleeping. Like you don't know, you can't tell until you actually measure, look inside the room and peer inside. So that's what superposition is. Yes, the actual story is much darker. So Robert, you make a very good point, but isn't the cat either awake or sleeping in reality? Yes, but atoms don't operate like that. If the actual, my cat is also sleeping right next to me, I think. Yep, my cat's still asleep. Yeah, when atoms actually work in the real world, we don't know what state atoms are is until we measure it, until we actually see it. And you'll see the word collapse used in the chat. That's what it means to collapse. So it makes no sense, but it's just how the universe works. We can't really change that. So superposition. Since qubits can operate in this complex number space, this is what it means to be in superposition. So if we go back a few slides, I'm going forward a few slides. So if we go back a few slides, this complex number space is kind of continuous, and continuous just means it's almost near infinite. It's basically infinite. So these qubits, when they're not 0 or 1, they can be an infinite number of possibilities. And that is like the mathematical definition of what it means to be in superposition. We can't measure it. We can't work with complex numbers on our actual computers. So when we say something is in superposition, we just mean it's a complex number. It's not 0 or 1. We can't do anything with it. It becomes 0 or 1 when we measure it. So right here, when we measure a qubit, they collapse to a discrete value, which is 0 or 1. Discrete just means like a finite. So let's see, I have a qubit and it's floating somewhere over here. It's in like this, whatever this complex number is, and it's just sitting there in my little chip. And I click a program that's going to measure my qubit. It's going to settle on 1 or 0. And we can estimate the probability of that, and I'll show you how in a second. But that's essentially what the mathematical meaning of what it means, superposition. So this is one of the things that's really hard to describe quantum mechanics, is that language, if that doesn't really make sense to you, blame language, blame English language. Language struggles to describe quantum phenomena and quantum mechanics. And you're going to see this limitation of language come up when we talk about entanglement and teleportation. So does anyone feel confused about this so far? Because understanding this is really important for entanglement and teleportation. And I don't want to move along and then kind of you don't understand the rest of it and you feel like, I got nothing out of this talk. So it's really important you know superposition. So I'm going to assume the silence in the chat is a good thing, and I'm going to move forward. So if you have a question about it later, go ahead and ask. Yeah. Yeah, definitely. It is quite literally magic. So since we're not observing the qubit directly, since you're not looking at your cat in the room, your cat is both asleep and awake because you don't have a camera in the room. It's just a dark room. You don't know what's going on inside that room. So the cat is asleep and awake at the same time. And when you open the door, you find out if your cat was 1 or 0, sleeping or awake. So until we actually measure the atom, we don't know what state it is. So remember that equation I told you about before? It's a probability. If you've taken any sort of probability or stats class, when you know that probabilities add up to 1. This is not 100% true, but this works. This analogy works for now. So this pair of qubits, so given a qubit that has these 2 bits, it has a, like this absolute value to the square, whatever, a probability of collapsing to 0, and b squared absolute value has this probability of collapsing to 1. So I'm going to give more examples about that in a second, but this is really important. This adding up to 1 is going to be like the basis of later entanglement and teleportation. So as you know, complex numbers, if we make them uncomplex, that's a terrible way to phrase it, we can kind of get them to add up to a certain value. So here's some examples. 1, 0 has a 100% chance of collapsing to 0. If this is confusing to you, remember A, B. This A denotes the probability of collapsing to 1, and B denotes the probability of collapsing to 1, 0. I flipped that around. Sorry about that. So this is what it means to be in superposition. 1 square root of 2 and 1 over the square root of 2 is the 50-50 chance. That's what it means to be in superposition. So when I said the cat is behind the door, it's a 50-50 chance. Is the cat asleep or is the cat awake? And you can kind of modify that probability. You can have a 70-30 chance, stuff along those lines. But you can't measure this on a computer. As you'll find out later, there are some classical computers that help with quantum computing, but to actually run your programs and run your machine code and everything, you need a 0 or a 1. This 1 over the square root of 2, what does that mean? Your computer can't understand that. So when it means to measure a qubit, it collapses to something we can understand. So this is still going to be kind of like magic. This is all of quantum computing. But this is the mathematical definition of what it means to be in superposition. So, yep. You don't need to understand this. So when we actually write quantum programs and we talk about quantum programs, we use something called quantum circuits. Much like designing a circuit for an actual computer, that's essentially what you're doing. But in this case, the circuit is your program. So this is a quantum program that does something. I have no clue what this does. I pulled a random image off Google to use for this slide right here. But this is the notation you're going to see we use later to make our little quantum circuit and our quantum program. So does anyone still feel confused about this? Like why this adds up to 50-50? Does anyone feel confused about that? It's okay if you kind of feel confused, but yeah. So this is like the mathematical definition of what something means to be in superposition. And now we're going to jump into I was talking about the Nand Gate in the beginning for the classical computing. So the controlled NOT gate, so the C-NOT is basically quantum computing's version of the Nand Gate. It is super important to kind of build up quantum computers. It's a fundamental building block of quantum computing. And all it does is, it's better if I actually do I have an example? Yeah, I have an example right here. It takes 2 qubits, like we saw earlier, like an A and a B. One is the control and one is the target. And it's like an if statement. If control is 1, which is true, so if control is 2, you just flip the target bit. So if the target bit was 0, it becomes 1. If it was 1, it becomes 0. Yeah, so if the control is 1, oops, that's a typo. That should stay 1. But the target bit was flipped because the control was true. That's all the C-NOT gate does. So it's okay if you don't understand that, if you still haven't taken CDA, or if you're still in the CDA right now. It's not super important you know this for the rest of the slides, but just so I can explain it for those who want some extra knowledge. And this is how it's represented in a circuit. And this is, if you care about the linear algebra, this is the linear algebra of it, the kind of matrix that you multiply against. So the next gate we're going to learn is the Hadmar Gate. It takes a qubit that is a discrete value, either 0 or 1, and puts it into superposition. This is going to be super important for the rest of the stuff, because superposition is what it means, and what's like the big benefit of quantum computing. Something in superposition that we don't know its actual state is basically what gives quantum computing an exponential speed up over regular computers. And it's what lets us achieve quantum supremacy or quantum advantage over like very traditional like problems that are super hard to solve, that would take like years or the lifespan of the universe plus an extra billion to solve on a regular computer. So the Hadmar Gate, you don't need to know what it works. I don't even know how it works. There's just some fancy math. It takes just a regular discrete value and just turns it into superposition. So another one, I was mentioning earlier that qubits are like, they're an actual atom, so they're in a 3D space, since they occupy the same space that we occupy. So there is a z-axis to them, and this is not super important, you know this, but when I explain teleportation, the z-gate is gonna pop up, so I wanted to show you now. It just flips it by pi radians. So it's not crazy that you know this, but just so you do. All right. So we're going to get into quantum entanglement, the second of the three quantum phenomena. So for you, go ahead and take a guess or a whack at what entanglement is and how you think it works. So I think this is a fun one. This is one that you often hear along with quantum teleportation when people talk about quantum computing or quantum mechanics. So entanglement's definitely my like favorite of the three. Getting mixed up, yep, that's good. Nathaniel, oh no, that was not Nathaniel. Dennis, that is superposition. That's technically superposition. What you said, yeah. Nathaniel, but it's not a bad guess. I guess that like, not a bad guess. So quantum entanglement, again, remember that equation. I said it's going to be important. So two qubits are considered entangled if they cannot add up to 1. So, whoa, how does that make sense? Didn't you tell me earlier that like a pair of qubits must add up to 1? This is when quantum mechanics gets, breaks our understanding of the universe again. Not so much, not really. But yeah, quantum entanglement is when two qubits don't add up to 1, or like they either greater than 1 or less than 1. That's like the mathematical definition for qubits to be entangled. And they can be entangled, atoms or particles can be entangled over near infinite distances. And this is going to be really interesting when I describe some of the other cool things that entanglement pertains. But you can put them at two ends of the universe and they're still entangled together. The actual quantum mechanics behind this, I don't understand. So I'm not going to get super deep into the talk, but if you want to, the Wikipedia page does do a pretty good job of explaining quantum entanglement, at least the summary or the abstract part. So if you want to pull that up, because they're like, what does it mean for two particles to be entangled? But one really interesting property that is what makes entanglement like super important for quantum computing is that if you have two cats in two separate rooms and the cats are considered entangled, so the cats do not factor up to 1, cat 1 and cat 2, cat A and B. When I open the door of room 1 of where cat 1 is, and it's awake, then cat B is also going to be awake. I know the state of cat B because they both collapse onto the same value. And if that doesn't make sense, hopefully some more explaining will do. But this is what makes entanglement so cool and so crazy. If you have two particles and they are entangled and you measure one of them, the other one is going to be the exact same value. And that's what it's really useful. So one really cool thing about this is that they communicate faster than light. Though they actually don't communicate, that's a lie. They coordinate faster than light. Communicating faster than light actually breaks the laws of physics, but coordinating faster than light doesn't. And this is where the English language struggles to kind of properly explain quantum phenomena. So I can't say communicate. I don't want to confuse y'all. But so when two qubits when they collapse, so what it means to be collapsed, like I mentioned earlier, it's just when they're measured. So whenever you measure qubits that are in superposition, they collapse. So yes, the qubits are soulmates is a good way of describing it. So another analogy I've heard of things that are entangled is if you have two Minecraft games and both your Minecraft game is entangled, you and a friend, and you're going to start a new world. You're going to open up a new Minecraft world to play on, and it's entangled with your friend's game. When you click play, you and your friend are both going to generate the same random number. So that's another way you can view quantum entanglement, and how we entangle two particles or two qubits. I'm going to show you in the next slide, but you didn't think that was going to happen. But that's essentially what entanglement is. These two things, these two particles, these two objects have a connection together. Thank you. I thought the Comic Sans would really draw your eyes to it. There's definitely some more Comic Sans and fun surprises in the rest of the slides. So this is a fun part. This is going to be some critical thinking. How do you think we entangle two qubits? I've told you everything you need to know to entangle two qubits on a quantum computer. It has to do with the gates I showed. So I showed you there's two gates. So notice how I mentioned that the two qubits are considered entangled when they can't add up to one, when their properties are not added up to one. So how do you think we can achieve that? A hint, it does involve putting them in superposition. And then it involves one other operation. So we put them into superposition. Pedro is super close. So CJ and Pedro are very close. So this very great MS Paint illustration is you take two qubits, you put one of them in superposition, and then you run a CNOT on them. And as you remember earlier, CNOT, it takes a control bit that is 1 or 0. What happens when you pass it a control bit or a target bit that isn't 1 or 0? And that is essentially what's putting them in superposition. So this, you can put, not superposition, this is how you entangle two qubits together. And it's really simple gate, and we're going to be showing that gate off in the live coding experiment. So teleportation. I meant to have a slide before that asked you, well, how do you think we do quantum teleportation? So I'm going to go ahead and ask that right now, but instead I give the answer away. That's a good way of describing a Pedro branch prediction. I've never heard that one way before, but that's interesting. So, CJ, you mentioned an X gate earlier. I never explained the X gate in the slides, but here's one right here. It's just a flip. It's just a bit flip operation. So that's going to be important here for this one. But does anyone want to take a guess at what is happening in this quantum circuit? This is teleportation. So what essentially teleportation is exactly what it sounds. You pass the state of one qubit over to another qubit. You teleport from place to place. So that's what basically passing the state is. So another thing about teleportation is there's the no cloning theorem. So you can't clone anything with teleportation. You are essentially using up this qubit when you do that. So you teleport this state and you put it over there, but you're essentially using it up. It's not like you have another copy of it going forward when you teleport. And this is another quantum phenomena of the universe that we can take advantage of for quantum computing. So does anyone want to take a guess? This specifically, I kind of give it away right here, but if not, I'll explain more in a second. This gives me a quick water break. And if you are okay with being recorded, you can come on mic and give your answer. But just know that this talk is being recorded and will be uploaded to the Night Hacks YouTube channel. So if you don't feel comfortable with that, you don't have to.
Okay, I'll take a stab at it. So it looks like we're entangling, I guess you say we entangle 3. So it looks like we entangle 2 of them, and then we entangle another one to our third bit, our third qubit to the second one.
Mm-hmm.
And then magic after that. I have no clue what happens after that.
No, you got really close. So this is our teleportation bit. This is the one. This is just an arbitrary state. So this is, I think, called phi, is the Greek name for that. And you'll see this around in quantum computing textbooks. This is just an arbitrary state. So any complex number is 0 or 1. And so we're going to entangle these two qubits, and then we're going to entangle these two together. So this one, A is entangled with B, and then we're going to entangle our teleportation one with A. And then we do, I don't understand fully the reason for this. It's definitely explained in the theorem and some of the math, but essentially we run some measurements. Remember, the Z gate essentially just rotates it by pi on its z-axis. I don't know the necessity of that, like why we need to do that. But then after you measure, after some magic, you get the state that you from this qubit over here. So, and this is not faster than light. So since we're essentially communicating, this is the reason why this isn't faster than light on quantum computers is because we need some classical bits to help with this transfer, because of the way quantum computers are constructed, and also because this is like multiple operations, there is some communication involved technically. This isn't faster than light, despite it having like two properties that are faster than light. Because entanglement, when you entangle two qubits and they collapse them, you measure them, they communicate faster than light. And they measured that in labs. I was watching a talk on this, and the reason why we know this is because they measured it in the lab, which is wild. It's really crazy. So we're going to jump into the coding, and the coding is going to be really brief, and I'm going to show you some other things and some other resources. But before I go into the coding, does anyone have any questions about what you've learned so far? So we've talked about superposition, entanglement, and teleportation, and we talked a little bit about quantum computing. Yeah, so quantum computing is definitely really intimidating. When I was going to give this workshop originally in the winter, I had some family incidents that required me to cancel it, but one of the things I was also really nervous is like I was struggling to find a way to present the material. So I completely redid the slides for the spring version of this workshop because I thought the original version of the slides was just not fun. I hope this one was better. I think this one's better. And I think the information is much more focused and it flows a little bit better than the original version. So yeah, I'm going to go ahead and we're going to pull up. Thanks, y'all. It's not over yet, so there's still time to change your mind. But I'm going to go ahead and pull this up. All right. Oh, don't want you to see Discord. So one thing I want to tell you, so if you are let me pull up the chat again. Where'd the chat go? Cool. So NightHacks is offering an intro to Python workshop, as Chris mentioned at the top of the hour. So if you're interested in quantum computing, it would really help if you knew Python, because the library right here, Kiskit, is a Python library. It's a Python library that lets you create quantum circuits and go ahead and interact with a quantum computer. So before I kind of get started, how do you think you're going to get access to a quantum computer? I hope I'm not giving the answer away by some of my stuff up here. I'm going to pull this up. How do you think you're going to get access? You're going to write this quantum program, but yeah. Eustace, that's a good answer. I'm surprised. I wonder if UCF has a quantum computer. I don't think they do. I think we would have heard this already. I definitely would have brought it up because I probably would have heard it. But yeah. Yeah, you go ahead and you use a quantum computing service. So I mentioned that I do work for Microsoft. Yesterday, actually, Microsoft made their quantum computer public. I think it's called Azure Quantum. So I believe it's called, yeah, Microsoft opened up its quantum computing service for the public yesterday. I didn't plan that. I had no clue about that. I just happened to see it in the news. So you can use the Microsoft Azure Quantum Service, and they use a different language. So it was entangled with this workshop. That's a great joke. That's really good. Props. They use a different language than Qiskit and Python, and we're going to show that at the end. We're going to talk about, they use a language called Q#. So if you're familiar with C# or F#, those are Microsoft languages. They use a variation of that called Q#. So Qiskit is IBM's, and I think just an open source quantum computing library for Python. It's really easy to learn and use. It has great docs. They have a bunch of resources that I'm going to tell you about at the end. And they do have a summer school. So I think the summer school is something you can apply to. And every summer they bring on a bunch of undergrads to kind of just go through this free course that they offer. You can watch the summer school for free, but you can also just be a part of the live experience if you want. So Cool. So the way we're going to code quantum circuits, like I mentioned earlier, I'm currently experiencing an RSI injury yeah, let me go ahead and zoom in. That's a good suggestion. I'm currently experiencing an RSI injury in my left hand, which is the hand I mainly use to type with. So I'm going to go ahead, luckily, I can show you quantum circuits, like actually make them. So this is IBM's quantum experience. You can literally sign up for this as I'm talking. You can use a Google account, a GitHub account, no credit card or anything required. IBM makes this free for people to use. There are some caveats that we're going to show in a second. Like you can't just take advantage and use all the quantum computing services that you want. So this is the superposition gate, and we're going to go ahead and measure our 2 qubits over here. So we can add new gates to it too if you want, and they let you make that easy to they let you know where you put it so you don't mess it up. You can't mess it up. And there's a bunch of other gates that I didn't talk about. So you can go ahead and mess around with those. And I think you can even make like your own little custom gates. So like I said, this is 2 qubits that we're going to entangle together. We're going to put them in superposition, then we're going to have a C0, and then we're going to measure them. And interesting, you notice how this gives you a probability. So this is what IBM thinks is going to happen. And there's also some other vector information if this is something you care for. So we see what IBM thinks is going to happen is going to be state 00 with 100% probability. Does anyone want to explain why that's going to happen? And then we're going to run it, and then we're going to see what actually happens. I could tell you that this doesn't actually happen. I can spoil that answer. I'm also using this as a water break. It's very strategic question asking. We don't get a curve. So you notice I mentioned a caveat earlier. So IBM lets you have free access to their quantum computers, but they give everyone free access. And there's a limited amount of bits the quantum computers can have. So there's some quantum computers only allow for 1 bit. So this is 2 bits right now. And quantum computers in general, they don't have a lot of bits. When I was watching a talk from 2018, this 2018 talk, IBM's quantum computer was only 5 bits. So right now, if we wanted to use so let's try using a real quantum computer. This one has, whoa, look at that queue. This is other people who queued their jobs. So you go ahead, you design your quantum circuit. This is, I think, only 1 qubit. And this right here, this is something I forgot to mention, but this is what's called a quantum register, and this is the classical register. So if you mentioned, I kind of sprinkled it in a few times that quantum computers still need classical computers, or classical computing capabilities, so we can actually measure and run our problems. And this is what it means. It's a classical register, and we kind of measure the qubits on that register. And register just kind of like, you can think of like slots. So if you have like an inventory in a video game and you have 10 inventory spaces, this is your inventory essentially. You only have 2 inventory spaces. So I know register can kind of be like an intimidating term, but don't feel intimidated by it. So I actually don't know which one is the best. This is 1 qubit. I don't think I can run this. If you see the one I am right now, this is a simulator. So this is a classical computer simulating a quantum computer. It doesn't actually work that well, and we're going to run it on this one to try, and I want to try running it on a real quantum computer. I tried running it last night, and it said it would take 5 hours to run my job. So let's see if we can try running it on a quantum computer right now, if it's going to be a reasonable time. Yeah, so there are some priority accesses. I think I'm using like the wrong provider and everything and the wrong computer. But there are ways to get your job to run quicker. But as like you're learning quantum computing, definitely have like maybe homework planned. So you can like do a quantum circuit, wait for your homework, like do your homework, and then come back and see if your job ran. So I probably should have started this at the beginning of the talk. I should have thought that in hindsight, but that's okay. I will post the answers to this in the NightHacks Discord whenever this finishes. I'll share what happened there. But we're going to go ahead and do it on the quantum computer simulator. And we're going to run the job. So it's going to transpile our code, our quantum circuit, and it's already done. So let's go ahead and look at the results. So we see the results. It's 0, 0, and 1, 0. Uh-oh, what happened? And we're going to talk about that in a second. But before we do, we're going to just show some other stuff. Quasum. What do people think quasum stands for? I think someone's going to get it right, I'm pretty sure. And what you can see here, quantum assembly. Yep, there's even a quantum assembly language. You won't work with it, but it exists. So this is a quantum register. This is an array of 2, a classical register array of 2, so like 2 bits, and some other stuff. So like a Hadmar gate on the register 1 and a CNOT gate on register 0 and 1. So register 1 corresponds to register 2 because that's how you index arrays. And this is Kiskit. This is the Python language. As you see, it's actually really simple. You just have some import statements, and if you don't know what those are, the Intro to Python workshop, I imagine, will cover them. Definitely someone from Nighthacks, correct me if I'm wrong. You just make some objects. So if you're in Intro to C, these are structs. If you're in OOP or later, these are just classes or objects. And you just add your Hadmar gate. You add your control NOT gate, that's what CX is, and you just measure them. And that's it. Writing a quantum circuit is really easy and really simple. You saw all that low-level stuff, but there's not actually a lot of low-level stuff you have to do in the actual programming thing. And that's another really cool thing about quantum computing. If you're someone that enjoys low-level programming, so you like working in C, or you like the idea of solving like hardware problems, quantum computing has this really cool middle ground that you're operating in a low-level space. You have to think low-level, like you have to think on the bit level, but you're still getting to use a high-level language like Python. And you're also working in quantum, which is really cool. So there's that. And this is, you can ignore what it means transpiled if you wrote some code and just the service will just transpile it. It's exactly the same in this instance. So we're going to go back to our results. So it gives you your results right here, nice and easy, and then also some interesting stuff if you care. And you could see 51% of the time, like we're dealing with probabilities here, it was 0, 0. But 48% of the time, it was 1, 0. But hold on a second. If I'm like in superposition and entanglement, like if you, Anthony, you told me if 2 qubits are entangled, they're going to collapse on the same value. What's going on? These are 2 different values. Do people want to guess what happened? Because there's 2 answers, and they're both really cool. I'm going to give a hint to one answer. You're dealing with atoms. So Ryan, you got the first one. You got the first answer. No. So there's 2 reasons why we're getting like this answer. There's 2 reasons why. Well, there's 2 possible causes, I should say. That's the better way to say it. Ryan got one of them. So one of the reasons it's because this is a simulation. This is a classical computer simulating a quantum computer. So there's always going to be some errors. There's actually 3 answers why. I forgot. There's a third one that's not super important. But the first one is this is just a simulation of a quantum computer. So when you write your quantum circuit, and you're going to probably use a quantum simulation so you can get immediate answers, you're normally going to get some answers that don't make sense or like that you weren't expecting, and that's perfectly normal. That's kind of to be expected on this. So the quantum simulation is going to be wrong sometimes. The other answer why this might be wrong is quantum error correction or quantum errors. So we're dealing with atoms when you're dealing with quantum computers. So let's say I ran this on an actual quantum computer. This wasn't a simulator. This is a real one. You're dealing with atoms. And literally the smallest cosmic ray that's just from the Big Bang passing through the universe or passing through the Earth can make your experiment wrong. It can make your answer wrong. And quantum computers have a lot of error correcting bits. If you're into networking and stuff like that, if you're an IT major, or if you heard about networking and how do we correct for error and stuff like that, how do we correct for error when we transfer packets around, it's kind of the same like thinking applies. Literally, literally. Why does my code have bugs? Cosmic ray. So a cosmic ray can like put your bit off the where it was supposed to be. So that can actually happen. So that's one of the two reasons. The third, less exciting reason is how you initialize your qubits. So this simulator initializes them both as 0. So they're both going to kind of like collapse on 0 most likely because like some of the math behind it. I'm going to hand wave some of that stuff. But yeah, it's also how you initialize your bits might also kind of lead to like a stray and like leading to a certain answer over the other. But you literally cosmic rays like quantum errors on the particle level, and also because you're running on a simulator. So that's why. So we're going to go ahead. I'm going to try some live coding. Where's back? We're going to go back here, and we'll make a new one. Where's the new button? I don't know where it is. So we'll just go back here. Click. So we're going to go back to my slides. Move this around. And I'm going to try, I think I lost my slides. I think I exited out of my own slides. Sloppy. One thing while I pull these slides back up on another tab, so you don't see my Google Drive as I'm doing that. If you're interested, if this was some stuff that you really liked, I'm going to talk about more resources at the end. I mentioned the Kiskit Summer School, something you should definitely check out if you found that interesting. It's an entire program for undergrads. The IBM and Qiskit scientists take you from not knowing anything about quantum computing to writing quantum programs and pretty cool stuff at the end of it. The lectures are also available online. So they're available on YouTube. They are pretty, like, I was going through them. I found them kind of tough, but I'm also bad at math. They definitely kick off with some linear algebra right off the start, but apparently you only need to know how to multiply two matrices. Ah, CJ, you went through it? That's really cool. Or I'm guessing you went through it, if that's what you recommended. That's awesome. Yeah, they have an entire syllabus here, and I believe they're accepting applications. Doesn't look like they're accepting applications yet for 2021, but definitely do it. It's going to be virtual this year again, I imagine. I imagine it's virtual every year. So if that's something you found cool, and it's something you can put on your resume, you can put it in the experience section. You went through a summer school on quantum computing. That's a great resume talking point if that's something you're trying to build, even if you never end up doing quantum computing for your job. So also this textbook, Quantum Computing for Computer Science, this is a talk based on the textbook by Microsoft Research. My slides were based on this talk, so it's like a game of telephone. This talk is definitely longer and goes into more of the math, and it also explains quantum computing through a state machine. So if you know what a finite state machine is, if you're in discrete 2, this is definitely a really nice deeper dive into quantum computing, and it goes over a problem and everything too, and it talks about stuff like reversible computing and how that relates, and it goes through some code at the end. It goes through Q# specifically, and to go ahead and design the quantum circuit. But yeah. And also I want to just shout out Microsoft Learn. So the Microsoft Learn website, or docs.microsoft.com, they have entire resources on quantum computing. So just right over here, it's called the Quantum Development Kit. If you try searching up quantum, you won't get it, but they have entire little modules that you can go through. They give you little time limits. If you remember at the beginning, I mentioned you can search a list and square root of n time, and you're like, whoa, that's super cool. You can do this module right here, which talks about the algorithm I was talking about, Grover search, and it has you code it up and everything. And you use Q#, which is pretty similar to C#. And C# is pretty similar to Java. So if you know Java, I think you're welcome to get started. So, yep, there's those resources. And I'll go ahead and drop those into Discord and drop those in the Zoom chat after I'm done over here. So let's see, what I wanted to do is I wanted to code the teleportation gate. I actually don't know how this is going to go. We're going to do some live coding. And if you were wondering why I had this up, I needed a whiteboard. So in case I needed to explain something, you can go to a Windows 98 simulator and use it. So that's pretty fun. That's how I made you saw some stuff in the slide earlier. So let's unzoom. So let's go ahead and design. If you want me to put a random gate in here, go ahead. I'll try putting a random gate. So let's go ahead and try recreating the quantum teleportation gate. I think I'm getting it. And if you have any questions you want to go ahead and ask, go ahead now. Now's a great time as I piddle away at this. So, and if you found that interesting, awesome. Definitely make sure, Chris, is there a sign-in that folks need to do, or is that's not happening?
There is not, but there's a feedback form at the end.
Awesome. Yeah, definitely give feedback. Definitely let me know how I did. If Night Hacks needs to bring me back, or they're like, nope, never bring that guy back. He was really crazy. So I hope you enjoyed it. This is kind of just the end of the presentation. I was going to talk more about resources. I didn't want to get too deep into quantum computing, partially because I felt like I might not be able to answer some of folks' questions and everything, because I'm definitely not an expert, like I mentioned at the top. But also, it's kind of a snooze fest. If you go really deep in quantum computing, not like an insult, like I really struggle to pay attention, but I just have a hard time paying attention. I'm trying to find the Nand Gate here. But yeah, I think we're just going to end it there, and I'm going to write this quantum circuit and share it in the Discord when I'm done, as I try to figure this out. But yeah, that's the whole presentation. That's everything. Wanted to keep it short. So if anyone has any additional questions, I'm happy to answer them.
Real quick, thank you so much, Anthony. That was a great presentation.
Thank you.